Consider the old half-filled glass of water, a classic test for whether you're an optimist or a pessimist. Is it half full or half empty? For a mathematician, neither answer is really all that interesting. They just aren't precise enough. Instead, mathematicians are much more interested in concrete details, like how much water could the glass hold, or how do we know where half its capacity is, or what amount of space is being taken up by the water. Questions like these might sound pretty specific for a glass of water, but knowing how much space things occupy is important because, well, that's sort of what the whole universe is. Space with objects in it. In the 3 dimensions that we're familiar with, the way we measure the space that stuff takes up is called volume, and it's another way math helps us get to the heart of objects that make up the world around us. I'm Jason Guglielmo, and this is Study Hall Real World College Math. In this next stage of our tour of geometry, we officially step into the realm of 3-dimensional objects. The last couple of episodes, we've looked at ways of measuring the amount of space different shapes take up in terms of length and area. That lets us tackle all kinds of problems with objects and the 2-dimensional space they occupy. And in many ways, the idea of volume shares a lot of the same concepts, just in beautiful red and blue 3D. Specifically, volume is the amount of space an object occupies in all 3 dimensions, which are the different directions in space. While the areas we explored before only had directions like left, right, and up, down, which we usually call width and length, now height comes into the mix too. And the larger the volume of an object, the bigger it is. As we've seen, the perimeters we've looked at were in units of length, and areas were in units of length to the power of 2, or squared, because they involve 2 measurements. To continue that trend, volumes are in the units of length to the power of 3, or cubed, since they occupy space in 3 dimensions. Like if we're talking about some object in units of meters, its volume will be in terms of meters cubed. As we saw when looking at surface areas last episode, it's easier to understand the idea of volume by looking at some specific simple shapes and how we might calculate their volumes. Which brings us to Abshir, an eco-friendly toy designer who's interested in exactly that. Abshir designs wooden block sets, the kind little kids love to play with. His latest model is a set of medieval castle building blocks made from colorful wooden pieces. While wood is fairly sustainable as materials go, Abshir is still conscious that chopping down trees isn't great for the planet. So he negotiates with his company, Tokita Toys, that for every tree used to make the building blocks, the company will agree to plant double that number. That way, they can help maintain forests and continue to capture lots of carbon from the atmosphere. To do this, Abshir needs to work out how much wood is in each block of his new set. Ultimately, that means he needs to calculate the volume of wood needed to make each block. First up on Abshir's roster of blocks are the pieces that make up the walls and doors of the castle. They're a simple box shape, known as a rectangular prism, which we also talked about last episode, that are 2 centimeters in width, 2 centimeters in length, and 4 centimeters in height. It turns out the formula we previously picked up for the area of a rectangle gets us very close to the formula for volume. We started by overlaying a grid on our rectangle and counting up how many squares fit inside. And we also noted that this is the same as multiplying the length times the width. For instance, one face of Abshir's blocks has 2 rows with 2 squares each, so the area of this face is 4 centimeters squared. But a whole rectangular prism also extends all the way in the direction of the height of the stack. So we could imagine filling the entire prism with small cubes, like when we used a grid to find the area of a rectangle. And we could add up all of those cubes. Here, Abshir's blocks would have 4 layers that each contain 4 smaller cubes. That means that just like with area, to get to a volume, all we need to do is take the area of this rectangle and multiply it by the height of the prism. That means the volume of any rectangular prism is its width multiplied by its length multiplied by its height. So Abshir can work out that these blocks each use up 16 centimeters cubed of wood. In fact, this idea of starting off with an area of some face and multiplying it by the height of our 3-dimensional shape applies to other objects too. For example, think about the cylinder we encountered last episode, which is the shape of the blocks that make up the towers in Abshir's castle. In this case, the radius of the cylinder is 1 centimeter and the height is 5 centimeters. Now imagine if we were to slice the stack at some point like a roll of cookie dough. We always end up with the same circle. So since we know the area of a circle, we can use the same trick we used for our rectangular prism. Then to get its volume, we multiply the area of the circular face by the height of the cylinder. In this case, that comes out to about 15.7 centimeters cubed. You might see a pattern emerging. We start with one face of our 3D object. It's a particular shape that extends in some direction, and if we make a flat cut at any point along that direction, we'll find the same shape as the original face. In general, we call these prisms. A cylinder is just a circular prism, just as the rectangular prism had rectangles on its faces. But there are other kinds of prisms too. You can have a triangular prism, which has a triangle on each end, a trapezoidal prism, or even a star prism. Just as we saw for other prisms, their volumes are all calculated by taking the area of the shape at the end of the stack, whether it's a rectangle, triangle, or something else, and then multiplying it by the prism's height. And this trick always works so long as the shape at the top and the bottom are the same, and it is consistent all the way through. It's a strategy that works in a similar way in lots of situations too. Like, the knowledge of prisms helps Abshir out with a whole bunch of block volumes, such as the battlements and rooftops of the castle. But he also has some blocks for the tops of the turrets in his castle set that aren't prisms. These blocks start off at the bottom in some shape, like a rectangle or a circle, and then shrink up to a single point at the top. Shapes like these are called pyramids in math lingo, although sometimes that's only used to refer to the kind with a square base. But technically, you can have pyramids with a base in the shape of a rectangle, or a hexagon, or any polygon. But when the base is a circle, we call it a cone. Looking closer at these shapes, they look kind of like our prisms. If we make any slice parallel to the bottom, the shape we get almost looks the same as the shape at the base, only it gets smaller the further up we go. Remarkably, there's actually only a small tweak we need to make to our formula for prisms in order to calculate the volumes of shapes like pyramids. To see it in action, let's consider a particular square-based pyramid Abshir is interested in, which makes up the top of the smaller turrets in the castle. The width of the square at its bottom is 3 centimeters, while its length is 6 centimeters. Now, if this were a prism with a square base, we'd get its volume by multiplying the area of the square by the height of the prism, because each layer of the prism is exactly the same. Here, it turns out, the only thing we need to do to change this formula so it's accurate for a pyramid is to multiply it by a third. Why is that the case? Well, the answer involves some more detailed math that's outside the scope of the series. If you're curious though, we've left a link to a full explanation in the description. Basically, it relies on thinking about slicing up the pyramid as a series of layers, kind of like our prism. But this time taking into account the fact that each layer shrinks the further up the pyramid we go, and considering how to add up over all the layers. Anyway, for these turret topping blocks, their volume would be a third times the area of the square times the height of the pyramid. That's 18 centimeters cubed. As for the cone-shaped pieces, it's a similar story. We simply take the area of the circle times the height of the pyramid like we're finding the volume of a cylinder. But then we multiply all of it by a third. And with this handy piece of math under his belt, Abshir can work out the volumes of the blocks at the top of the turrets and how much wood they use up. There's one final kind of block for Abshir to work out the volume of his ingenious castle design, the dome that makes up the top of the central palace. Having designed the set, he knows that this shape is just a sphere cut in half. That means its volume is half of a whole sphere, with a radius of 4 centimeters. That turns his problem into a slightly different one, which is working out the volume of a sphere. Once again, I gotta come clean. The math behind where the formula comes from gets pretty involved, so we won't delve into the whole thing here. But we'll leave some details for the general idea of how we calculate the volume of a sphere in the description, which actually uses what we just learned about pyramids. At any rate, we end up with a formula that only needs a single detail about the sphere to calculate its volume: its radius. The total volume is 4/3 times pi times the radius cubed. And with that, Abshir can work out the volume of his dome. For the entire sphere, it comes out to about 268 centimeters cubed. He then halves that for 134 centimeters cubed, since the dome shape only has the volume of half a sphere. Adding up all the volumes of his different blocks, Abshir can work out how much wood each block set needs, and that helps Tokita Toys know how many trees they need to plant. And with these methods for calculating volumes stowed away in our mathematical toolbox, we've covered the basic ways we measure space in 2 and 3 dimensions. While we've looked at properties of just a few specific shapes, the lessons we learned in these last few episodes actually apply in lots of more complicated geometric problems in all kinds of situations. That's the great thing about geometry. Studying just a few seemingly simple constructions gives us ways of handling more complicated physical structures and the spatial relationships that we encounter in everyday life. That's because a lot of the time we can break down a complex shape, or at least approximate it, in terms of simpler shapes. In fact, that's exactly what Abshir did with his castle. He considered the whole thing in terms of the individual blocks with simple shapes, then added it up to get the whole thing. But even if something isn't made of actual blocks, we can add up over different parts of a more complex shape piece by piece, like we did for areas in a previous episode. This idea forms a root of calculus, which is the math that lets us calculate areas and volumes of more complicated shapes formed by mathematical functions. In calculus, we slice up shapes into infinitely many tiny simpler shapes, which is another way of coming up with formulas like we did for our pyramids and the sphere. But for now, there's a much humbler little shape we still have plenty to learn from: the triangle, which is what we'll be turning to next episode. Thanks for watching Study Hall Real World College Math, which is produced by Arizona State University and the Crash Course team at Complexly. If you like this video, give us a like and subscribe. You can learn more about ASU and the videos produced by Crash Course in the links in the description. See you next time.